Hello, my curious friend, and a very warm welcome to the Deep Field channel. Tonight we're going to journey together across the most vast and silent territory in existence, that immense and almost unimaginable expanse that separates our galaxy from its nearest neighbour. It is a voyage that takes place entirely within the mind, and I promise to try not to make the subject so dazzling that it chases away the sleep you so richly deserve. But before we set off, I would love to know in the comments which corner of the world you're listening to me from tonight. And if laziness arrives before any words, just leave a simple hello. That small gesture tells the algorithm that this is a welcoming space and helps bring more tired minds to relax here with us. If you enjoy our scientific journeys, please also leave your like and subscribe to the channel. And to those who are already part of our community, my heartfelt thank you. If you wish to draw even closer, consider becoming a member. Members receive early access to videos before anyone else. The link is in the description. Now, wherever you are, find a very comfortable position. If sleep comes, accept the invitation. Let us begin. There is an experience that almost every human being has had, but which rarely anyone stops to examine carefully. It is that moment when you are outside on a clear night, far from the city lights, and you look up. The sky is full of white dots. Some tremble slightly like very distant flames. Others seem fixed, silent, sure of themselves. And for a very brief instant before daily life reclaims its place, you feel the scale. You do not understand it. You cannot measure it, but you feel it. Something in your chest recognizes that it is too vast to be contained by any word. What you're looking at in that moment is almost entirely the Milky Way. The overwhelming majority of stars visible to the naked eye belong to our own galaxy. They are, in cosmic terms, in the same neighbourhood as us. But there is a point or two in that sky that is not a star. It is an entire galaxy, a cluster of hundreds of billions of suns, so distant that it appears as a pale, barely perceptible smudge, almost an illusion. And between us and that faint point, there is something. Not the emptiness we imagine when we close our eyes and think of empty space. There is something much stranger, much more textured, much fuller than common sense allows us to suppose. The first thing we need to undo is the idea of a perfect vacuum. When the word space comes up in a conversation, the human mind almost automatically paints a dark, empty picture, a total absence. The place where no substance exists. This intuition is understandable, because that is what it looks like when we gaze at the night sky, but it is wrong in a rather fundamental way. Intergalactic space, that territory between neighbouring galaxies, is not empty. It is far from empty. It is filled with matter, energy, fields, structures, and phenomena that we have spent decades trying to catalogue and that still surprise us regularly. The most interesting question is not just what is out there. It is that the answer to that question has completely changed over the last century and continues to change. What astronomers of the early last century believed to be dead, content-free space gradually revealed itself to be one of the most complex and richly structured environments known to physics. Every new generation of telescopes, every new instrument capable of detecting wavelengths that human eyes would never perceive, brought with it a new layer of content where only supposed silence once existed. Let's start with scale, because without understanding the size of the stage, nothing else makes proper sense. The closest galaxy to the Milky Way that qualifies as a full galaxy in its own right, and not as a smaller satellite, is Andromeda. It is approximately 2.5 million light-years away. A light-year is the distance light travels in one full year, moving at about 300,000 kilometers per second. To give you an idea of what this number means in human terms, the light that leaves the sun takes about 8 minutes to reach us. The light that leaves the moon takes just over a second. The light from Andromeda that reaches your eyes tonight, if you are in a place dark enough to see it, left there 2.5 million years ago. At that moment, the ancestors of modern humans were still learning to use chipped stone tools in Africa. This interval of 2.5 million light-years represents the distance between us and a relatively close cosmic neighbour. In the context of the observable universe, Andromeda is right next door. The universe is about 93 billion light-years in diameter, and galaxies are scattered across this entire expanse in groups, clusters, and superclusters, separated by even greater immensities. The space between the local group, which includes the Milky Way, Andromeda, and a few dozen smaller galaxies, and the next large cluster of galaxies is already on the order of tens of millions of light-years. But let us return to the space between us and Andromeda, because it's already vast enough to reveal all the fundamental properties of the intergalactic medium. This space has a technical name, IgM, from the English intergalactic medium, and it has a characteristic that begins to contradict the intuition of emptiness from the very first moment you examine it. It contains gas. Not much, it is true. The density is extraordinarily low, something on the order of 1 atom per cubic meter on average. Compare this to the air you are breathing right now, which contains something around 25 times 10 to the 25th power of molecules per cubic meter. The difference is so many orders of magnitude that any everyday analogy fails miserably. But the gas is there, and this sparse gas, this trace of hydrogen and helium distributed through the void between galaxies, is the direct descendant of what the universe was right after the Big Bang. The young universe was almost entirely hydrogen and helium. These primordial elements spread in all directions as the cosmos expanded. Gravity gradually clumped this matter into clouds, and the clouds into stars, and the stars into galaxies. But not everything was captured. A substantial fraction of the universe's baryonic matter, the matter made of protons and neutrons, the kind of matter that forms you and the ground and the stars, remained between the galaxies. This intergalactic material is an archive. It is the physical record of how the universe was before it organized into structures. Studying it is like finding the original draft of a story whose published book is all around us. And the intergalactic gas is not uniform. It has a temperature, and this temperature varies in ways that would cause discomfort to anyone trying to imagine heat intuitively. In the colder, denser regions near the filaments that connect galaxies to each other, the gas can be at a few tens of thousands of degrees. This is already hotter than the surface of many stars. But in the more diffuse regions, heated by the radiation from galaxies and by the effects of shock waves from ancient energetic events, the temperature can rise to tens of millions of degrees. A gas almost non-existent in terms of density, but of extraordinarily high temperature, invisible to ordinary light, detectable only in X-rays. This diffuse hot gas has a name, the warm-hot intergalactic medium, sometimes called WIM. For a long time, astrophysicists knew that the amount of baryonic matter they could detect in galaxies and their immediate vicinity did not add up to the total predicted by cosmological models. There was missing matter, matter that should exist, but that telescopes could not find. The IM was the answer. A significant portion of the universe's atoms was hidden in this almost imperceptible gas, scattered through the spaces between galaxies, heated to temperatures that made it invisible at most wavelengths, but detectable in X-rays and ultraviolet. The search for this missing matter lasted decades and is still ongoing. Besides gas, the space between us and Andromeda is permeated by magnetic fields. This might seem surprising. We tend to associate magnetic fields with specific physical objects, with magnets, with planets, with stars. But intergalactic space possesses its own magnetic fields, extraordinarily faint but structured. The intensity of these fields is on the order of femtoteslas, a unit so small that it requires a chain of prefixes to be verbalized accurately. They are fields billions of times weaker than the Earth's magnetic field, and yet they exist, and they influence the behavior of the charged particles that cross intergalactic space. The origin of these fields is one of the open questions in modern astrophysics. Were they generated in the very first instance of the universe, even before the first stars? Were they injected into the intergalactic medium by galaxies through plasma jets? It is probably both, in proportions we're still trying to determine. And then there is radiation. The space between galaxies is not dark in the electromagnetic sense. It is bathed in photons of all energies. The cosmic microwave background radiation, the echo of the Big Bang, permeates the entire universe almost uniformly, including intergalactic space. Ultraviolet light emitted by quasars and active galaxies continuously ionizes the intergalactic gas, keeping the hydrogen in a plasma state in the most exposed regions. Cosmic rays, subatomic particles accelerated to speeds close to that of light, cross this space coming from origins we still debate. Neutrinos, ghostly particles that interact with matter so weakly that billions of them pass through your body every second without leaving a trace, permeate intergalactic space in immense quantities. The stage between us and Andromeda is, therefore, an active, radiant, magnetized environment, replete with moving particles, not in the sense that the word full evokes when we think of a room or a cup, but full in the sense that every cubic meter of this space contains information, fields, particles, and energy. No region between us and the nearest neighbouring galaxy is truly separated from the rest of the universe. Everything is connected by these invisible networks of matter and radiation. And there is something else, something that astronomers of the early 20th century could not have imagined even in their most ambitious dreams. Most of the universe's content is not hydrogen gas, it is not stars, it is not galaxies, it is not magnetic fields. Most of the universe is made of something we cannot name precisely, something that does not emit light, does not absorb light, does not reflect light, and yet has mass, and this mass bends the geometry of the space around it. We call it dark matter because dark is the only honest word to describe something that does not interact with light in any way we can detect. And between us and Andromeda, dark matter is present in quantities that far exceed all visible matter combined. But the stage is not yet complete with these elements. There is a force that acts on this entire scenario, on the gas, on the dark matter, on the magnetic fields, on the galaxies themselves. A force that is not pushed by anything material, that has no identifiable source in the traditional sense, and that is making the universe expand in an accelerated manner. This force carries the provisional name of dark energy, and it permeates absolutely all space, including every centimetre between us and Andromeda. It is what dictates the rate at which this space is growing every moment that passes, separating distant galaxies from each other with a speed that increases over time. The question that hangs here, before we go deeper into this journey, is this: where does the energy that animates all this come from? The gas is hot, but something heated it. The magnetic fields exist, but something generated them. Particles cross intergalactic space at enormous speeds, but something accelerated them. The universe expands, but where does the impulse that sustains this expansion come from? There is an image that physicists sometimes use, almost jokingly, to explain the most disconcerting problem in modern cosmology. Imagine you light a campfire in a forest and then walk away. After a few miles, you still feel heat. After a few days, there are still embers. But when you go back to investigate the firewood, you discover it was all consumed a long time ago. The heat continues to exist without any apparent source to justify it. This is, in very rudimentary terms, the enigma of dark energy. The universe radiates accelerated expansion, and we cannot find the firewood that is feeding this bonfire. To understand where the energy that moves everything between us and Andromeda comes from, it is necessary to take a step back and recognize that the very concept of energy has undergone a radical transformation over the last few centuries. For a long time, humans understood energy as something that is seen, that is felt, that has an obvious source. The sun shines because it burns, the wind blows because the air moves, fire heats because it consumes. The idea that empty space could contain energy was considered absurd by many generations of thinkers, and even among last century's physicists there was a visceral resistance to this possibility. The story begins, perhaps, with a mistake that turned out to be a prophecy. In the early 20th century, Albert Einstein realized that his general relativity equations described a dynamic universe, expanding or contracting, and this bothered him deeply. At the time, the consensus was that the universe was static, eternal, motionless on a large scale. To force his equations to agree with this consensus, Einstein introduced an artificial term, a sort of mathematical constant that acted as a negative pressure, preventing gravity from collapsing everything. He called this term the cosmological constant and represented it with the Greek letter lambda. Years later, when Edwin Hubble demonstrated that the universe was indeed expanding, Einstein dismissed his cosmological constant, calling it his biggest blunder. The ironic, the disturbing thing is that decades later this same constant would return with a vengeance. Edwin Hubble was an athletic man with a deep voice who had left a promising career as a lawyer to pursue the stars, working at the Mount Wilson Observatory in California. With a telescope that was at the time the largest ever built, he spent night after night measuring the light spectrum of distant galaxies. What he found changed human perception of the cosmos forever. The galaxies were moving away, and the furthest ones were moving away faster. The speed of recession was proportional to the distance. This meant that space itself was growing, stretching like the surface of a balloon being inflated. The law that emerged from this work, known as Hubble's law, is the first of the fundamental laws governing what lies between us and Andromeda. Intergalactic space expands, and the rate of this expansion is measurable. But the expansion of the universe by itself does not explain the energy source of what exists between galaxies. For that, one must delve into something even stranger. Think of a musician tuning an instrument in a room full of people. Every person in the room is breathing, talking, moving. The air in the room is constantly in microscopic agitation. Even if the room were completely silent, the very atoms forming the air would be vibrating. Now imagine that this room could be emptied of every atom, every molecule, every particle you could extract. You would expect to find absolute silence, a total absence of energy. Quantum mechanics says you would be wrong. Even in a perfect vacuum there is energy. This is zero-point energy, the energy of the quantum vacuum, and it is one of the most serious candidates to explain what we call dark energy. Quantum mechanics developed over the first decades of the 20th century by a constellation of minds that included Werner Heisenberg, Niels Bohr, Erwin Schrödinger and Paul Dirac, revealed that the universe at its most fundamental scale is radically different from what the senses suggest. The most disturbing law of this set of revelations is Heisenberg's uncertainty principle. In terms that resist simplification, this principle says that certain pairs of physical properties cannot be known simultaneously with absolute precision. The position and momentum of a particle, for example, have a fundamental imprecision that is not a matter of bad instruments, but of the very nature of reality, and this uncertainty has a direct consequence. It prohibits the vacuum from being truly empty. In any region of space, even in a place where there is nothing, pairs of particles and antiparticles spontaneously emerge from nothing and annihilate in fractions of a second. Space boils, invisibly and constantly, with creation and destruction. These pairs of virtual particles, as they are called, are not poetic speculation. They have measurable effects. One of them is the Casimir effect, demonstrated experimentally with remarkable precision. If you place two metal plates very close together in a vacuum, with no applied electric field, with no mechanical force, they attract each other. This happens because the vacuum fluctuations between them are suppressed by the proximity of the plates, while on the outside the fluctuations remain full. The energy imbalance pushes the plates against each other. The force of the vacuum is real. The energy of the vacuum is real, and it exists throughout intergalactic space, in every fragment of the abyss between us and Andromeda. The problem, and it is a problem of truly cosmic proportions, is that when physicists try to calculate how much the quantum vacuum energy should contribute to the expansion of the universe, the numbers disagree with the observed numbers by a factor that has no precedent in the history of physics. Quantum field theory, which is the most precise framework we have to describe the fundamental forces, predicts a vacuum energy density that is dozens of orders of magnitude greater than what cosmological observations indicate. This abyss between theory and observation is called by some physicists the worst prediction error in the history of science. Something is wrong, profoundly wrong, and no one knows exactly what. The history of this perception reached its dramatic climax in the late 90s of the last century. Two independent groups of astronomers were measuring the expansion rate of the universe using a special type of stellar explosion called a type Ia supernova. These explosions have a known intrinsic luminosity, which allows calculating precisely how far away they are. Saul Perlmutter led one group, and Brian Schmidt and Adam Rees led the other. Both groups arrived at the same disconcerting result. The universe was not just expanding, it was expanding in an accelerated manner. The distant supernovae were fainter than they should be, which meant they were further away than expected. Something was pushing the universe outward, countering gravity, and it was doing so faster and faster. In 2011, the three received the Nobel Prize in Physics for this discovery. The name established for the cause of this acceleration was dark energy, and it corresponds to approximately 68% of all the energy content of the universe. The fundamental imbalance that makes intergalactic space work the way it does is, at bottom, an asymmetry between forces. Gravity pulls, it wants to contract, collapse, gather. It is an attractive force without exception on normal scales, and during the first billions of years of the universe it dominated, forming stars, galaxies, clusters. But dark energy pushes. It permeates the vacuum with a negative pressure, a tension that acts in the opposite direction to gravitational attraction. And because dark energy is spread evenly throughout all space, while gravity concentrates in regions of high density, a point comes when the universe dilutes enough for dark energy to win. That point has already been crossed. We are living in the era of dark energy dominance, and this domain must grow over time. But dark energy is not the only law governing the space between galaxies. There are others, more familiar in name, less familiar in scale. The law of conservation of energy, formulated in different ways by Julius Robert von Meyer, James Prescott Joule, and Hermann von Helmholtz in the 19th century, says that energy is neither created nor destroyed, only transformed. This law governs everything, from the flame of a candle to the radiation of a quasar. The gas that exists between us and Andromeda is hot because energy was injected into it at some point, whether by supernova explosions, black hole jets, or shock waves that travelled through intergalactic space. This energy did not come from nowhere. It was transformed from one form to another, and the traces of these transformations are imprinted in the temperature, ionization, and distribution of the intergalactic gas. Thermodynamics, especially its second law, also has something to say about the space between galaxies. This law, which speaks of the inexorable increase of entropy, tells us that physical systems naturally tend towards disorder, towards the uniform distribution of energy. The intergalactic gas, as it disperses into the vacuum, as it slowly cools over billions of years, is obeying this law. The magnetic fields that structure this gas are islands of order in a sea of growing disorder. Maintaining this order costs energy, and the bill is paid by the very dynamics of the expanding universe, which generates flows, shocks, turbulences capable of continuously reorganizing the intergalactic medium. Newton's law of universal gravitation, later refined by Einstein's general relativity, governs how dark matter shapes the space between galaxies. Dark matter does not emit or absorb light, but its gravity is real and powerful. It created the filaments and walls that structure the universe on a large scale, the so-called filaments of the cosmic web, and it is along these structures that the intergalactic gas is distributed. The law of gravity, in this sense, is the invisible architect that decided where the gas could exist and where the vacuum would be deepest. Electromagnetism, described in James Clerk Maxwell's elegant equations in the 19th century, governs the magnetic fields that permeate intergalactic space. Maxwell was the first to realize that electricity and magnetism were faces of the same phenomenon, and that electromagnetic waves traveled at the speed of light, but his equations are not limited to radio waves or visible light. They also describe how magnetic fields are generated by currents of charged particles, how these fields resist compression and propagate through space, and how they interact with the intergalactic plasma in ways we are still learning to measure. There is a mechanism that illustrates all this particularly vividly. When a galaxy ejects a relativistic jet, a beam of plasma and energy launched by the poles of its central black hole at speeds close to that of light. This jet travels through the intergalactic medium like a projectile passing through water. It compresses the gas ahead of it, heats regions that were cold, amplifies local magnetic fields through the process called compression and shear, and injects high-energy particles that later disperse through space like a mist of radiation. Every active galaxy that exists between us and Andromeda is, at this very moment, carrying out this process to some extent, transforming gravitational energy into kinetic energy, into heat, into magnetic fields, into accelerated particles. A single jet of these proportions heats, magnetizes and reorganizes the gas of a region that can extend for hundreds of thousands of light years. But the space between two nearby galaxies contains dozens, sometimes hundreds of smaller galaxies, satellites, dwarfs, remnants of ancient mergers. Each of these structures has its own history of activity, its own effects on the surrounding medium. The question that hangs, quiet and heavy, is what happens when this process repeats millions of times, spread across volumes of space we can barely imagine, over a time that exceeds any human scale of reference. The answer to this question began to take shape not in telescopes but in mathematical models. It was when physicists stopped asking what exists at each point in space and started asking how these points relate to each other that the true nature of the universe on a large scale began to emerge. The transition was slow, uncomfortable, and required science to abandon a very old intuition that the cosmos in its totality should be smooth, homogeneous, distributed more or less evenly in all directions. This intuition was reasonable, it was elegant, and it was profoundly wrong. What galaxy surveys began to reveal over the last decades of the 20th century was a structure that no one had predicted with sufficient precision. Galaxies are not distributed randomly through space. They cluster into groups, and the clusters organize into superclusters, and the superclusters connect along filaments that span distances of hundreds of millions of light years. Between these filaments there is something that scientific language calls voids, regions of space almost devoid of bright galaxies, which can have diameters on the order of several hundreds of millions of light years. The whole of this, seen from far enough away that the human scale completely disappears, resembles a cosmic sponge or perhaps a web, or a network of bubbles whose walls are made of matter and whose interiors are made of almost nothing. This pattern received a name that carries all the ambition of modern cosmology, the cosmic web. And what makes the cosmic web extraordinary is not just its existence, but the fact that it emerged. No galaxy planned to occupy a filament. No cluster decided to position itself at a convergence node. No local law prescribed that empty space should empty out even further, while dense regions became even denser. All this resulted from processes that operated over billions of years, starting with tiny quantum fluctuations in the early universe, amplified by gravity, shaped by radiation pressure, modulated by forces acting on scales far below what any instrument of the time could detect. The order we see today is the accumulated product of an instability that lasted from the first moments of existence to the present. The Russian physicist Yakov Zeldovich, working in the 60s and 70s of the last century, was one of the first to mathematically anticipate that the gravitational collapse of matter should not produce symmetrical spheres, but rather flattened structures, sheets of matter that he called pancakes. Zeldovich's model was an abstraction, an approximation, but it contained an essential truth. The geometry of gravitational collapse in the expanding universe does not favour symmetry. It favours flattening, elongation, concentration along preferred axes. The filaments we observe today are, in a sense, the descendants of Zeldovich's pancakes, regions where matter flowed along preferential directions and accumulated in long, thin structures. But Zeldovich's geometry was only a step. What came next required computers, and computers took decades to become powerful enough. The first numerical simulations that tried to reproduce the formation of the cosmic web emerged at the end of the last century, and when the results began to appear on the screens, the astonishment was immediate and almost unanimous. The structure that emerged from the gravitational equations applied to a perturbed homogeneous universe was extraordinarily similar to what telescopes were beginning to map: filaments, nodes, voids, walls of galaxies. Everything was there, produced not by any special instruction, but only by gravitational dynamics operating over sufficient time. The Millennium Run project, carried out in the first decades of this century, was perhaps the most ambitious step in this direction. A simulation that tracked the movement and interaction of billions of dark matter particles over billions of years of cosmic time, producing a virtual universe whose large-scale structures were almost indistinguishable from the observed ones. Dark matter, which does not emit light and does not interact with electromagnetic radiation, was the most important computational ingredient because it is what forms the gravitational skeleton upon which ordinary matter, gas, stars, galaxies, accumulates. Without dark matter, the simulation produced a much smoother, much less structured universe, completely inconsistent with what we see. What this means for the space between us and Andromeda specifically is that this space is not a homogeneous void crossed by particles and fields randomly. It is embedded in a structure. The local group to which the Milky Way and Andromeda belong is located in a specific region of the cosmic web, a region that astronomers have identified as belonging to the Laniakea supercluster, a structure that extends for about 500 million light-years and contains something on the order of 100,000 galaxies. Within Laniakea, the local group occupies a relatively peripheral position, close to an emptier region, a void called the local void, which exerts a negative gravitational pressure on the movement of surrounding galaxies. This location is not irrelevant to understanding the space between us and Andromeda. The movements of galaxies within Laniakea are not random. They flow, like rivers following the gradient of the gravitational potential, towards the densest regions of the supercluster. Andromeda and the Milky Way are approaching each other partly because of their mutual attraction, but also because both are embedded in a force field that goes far beyond their individual masses, the gravitational background of the supercluster, the pressure of the void behind, the attraction of the matter concentrations ahead. All this contributes to the movement vector of each galaxy. The space between them carries the memory of these forces in its geometry. The geometry of the space between two nearby galaxies is, therefore, a geometry that inherits information from larger scales. The local intergalactic medium is not isotropic. It has preferential directions along which the gas flows more easily, magnetic fields that have been stretched and aligned by these flows over billions of years, filaments of denser matter that connect the galaxies of the local group to each other like thin threads of a web. Radio and X-ray observations have begun to reveal these filaments, structures that are extremely difficult to detect because they contain very faint and very hot gas, but which are real, measurable, and carry significant amounts of baryonic matter that for decades was lost in the universe's matter balances. Astronomers have called this material the warm-hot intergalactic medium, using terminology that captures both the relatively modest temperature compared to the interior of clusters and the general state of ionization of the gas. This medium exists in the filaments that connect galaxies, and its temperature, its density, its chemical composition are the result of the entire history of activity described in the previous part multiplied by scales that exceed any simple intuition. Every jet from an active nucleus, every supernova, every stellar wind that escaped beyond the galaxy contributed over billions of years to the current state of this material. The filament between the Milky Way and Andromeda, if it exists with sufficient density to be detected, is the accumulated archive of everything that has happened to these two systems since they formed. Rotation also plays a role that science is still learning to quantify precisely. Galaxies spin, and this spin does not end at the visible edges of the stellar disk. The dark matter halos that surround each galaxy also have angular momentum, and this angular momentum was acquired during the gravitational collapse that formed the galaxy, through tidal interactions with neighbouring structures. The theory that describes this process is called tidal torque theory, and it predicts that the axis of rotation of a galaxy must have some correlation with the geometry of the filament in which the galaxy is embedded. Galaxies and filaments tend to have their rotation axes aligned in specific ways with the direction of the filament, not perfectly, not deterministically, but with a statistical tendency that is real and measurable. This means that the organisation of the space between neighbouring galaxies is not just a matter of matter distribution, it is also a matter of rotational geometry, of alignment of angular momenta, of correlations between the orientations of structures that are separated by millions of light years. The cosmos has orientational memory. Galaxies carry in their spin information about the way matter flowed along the filament in which they were born, and the space between them carries, in its magnetic fields, in its gas flows, in the orientation of its shocks, the mark of these long-distance correlations. When Brent Tully and his team identified and mapped Laniakea in enough detail to publish their results, what became clear was not just the scale of the structure, it was the elegance of the method. To map a supercluster, Tully and his collaborators did not just look at where the galaxies are, they looked at how the galaxies move. The so-called peculiar velocities, the deviations from pure Hubble expansion, reveal the underlying gravitational field with a precision that static position alone does not allow. A galaxy that is moving towards a mass concentration is being attracted by something that does not need to be visible to be real. By following these movement vectors, following the flow lines of the gravitational field to their attractors, it was possible to trace the boundaries of Laniakea as a cosmic watershed, a region whose galaxies tend to flow towards a common centre of attraction called the Great Attractor. The beauty of this map is not decorative. It reveals that the organisation of the universe on a large scale obeys a logic that is at the same time simple in its principles and extraordinarily rich in its consequences. Gravity, time, and the initial conditions of the early universe are enough to produce all the complexity we observe. There is no need to invoke any additional law, no external agent, no organising intelligence. The structure emerges from the dynamics, and emerges in a way that can be calculated, predicted, and compared with observation with a precision that still surprises us. But here we encounter the limit of what gravity and time alone can explain. Simulations that include only dark matter and gravity produce structures that resemble the observed ones in broad strokes, but that diverge in the details in ways that are physically important. The filaments are less complex than the real ones. The voids are simpler. The temperature distribution in the intergalactic medium does not correspond to what X-ray and microwave telescopes detect. Something is missing, and this something is not small. It is important enough to alter the structure of the filaments, to heat the gas in the voids to temperatures that pure gravity cannot explain, to magnetize intergalactic space to intensities that gravitational compression alone is unable to produce. The patterns we described, the filaments, the nodes, the voids, the rotational geometry, the long-distance correlations, would be recognizable even without this ingredient, but they would be smoother, colder, more magnetically inert. The intergalactic medium would be a different place, and the boundary between galaxies and the void would be much less rich in structure than it actually is. What makes the observed patterns more complex, more energetic, more magnetized, hotter than pure gravity predicts, is a process that operates on much smaller scales, but whose effects propagate to larger scales, in ways we are still learning to quantify accurately. The amplifier has no poetic name. It is not an exotic, newly discovered substance, nor a mysterious force that physics still resists naming. It is something you have already encountered, something that appears in conversations about storms and engines and copper wires. It is the magnetic field. More precisely, it is the intergalactic magnetic field, that faint and almost impossible to measure presence that permeates the space between galaxies and that, against all intuitive expectation, manages to transform the behavior of a medium that would otherwise be just diffuse gas and silent gravity. The reason the intergalactic magnetic field surprises those who encounter it for the first time is precisely this. It seems too weak to matter. The most careful measurements we have, made through the analysis of the Faraday rotation of distant radio waves, suggest intensities in the range of a few femtoslas, a unit so small that it is hard to even pronounce without hesitating. A femtotesla is a quadrillionth of a Tesla. The Earth's magnetic field at the surface is around 50 microteslas, which means the intergalactic field is roughly a quadrillion times weaker. Compared to the magnetic field that holds a paper note to a refrigerator, it is infinitesimally smaller. It would be reasonable, then, to ignore it as irrelevant. But this intuition fails because the intergalactic medium is not like a refrigerator. It is a very low-density plasma, with particles so scattered that they rarely interact directly. In this type of environment, a weak magnetic field does not need to exert direct force on the particles to be important. It just needs to structure the space through which these particles move, and do so coherently over enormous distances. When a magnetic field is aligned along a cosmic filament for tens of megaparsecs, it is not the intensity at any point that matters. It is the coherence, the way the field maintains a consistent direction over distances that the mind cannot visualize without instruments. Think of a river current where the water flows slowly. A small pressure difference over miles might not move a stone at the bottom, but it can guide the path of anything that floats. Charged particles in the intergalactic medium are those floating things, and the magnetic field is the invisible geometry of the river. Electrons and protons that would otherwise disperse isotropically, in all directions with equal probability, are subtly channeled by the field. Over enough time, on scales of hundreds of millions of years, this subtle channeling produces enormous macroscopic effects. The amplification mechanism begins even before galaxies form the filaments we see today. The most detailed simulations of the intergalactic medium suggest that primordial magnetic fields, likely generated during or shortly after the rionization of the universe, were extraordinarily weak and disorganized. But as the intergalactic gas began to flow along the filaments of the cosmic web, dragged by gravity towards the intersections where galaxies form, this flow compressed and stretched the field lines. Compression increases intensity. Stretching increases coherence. Two processes operating simultaneously, one making the field stronger locally, the other making it more organized on a large scale. But there is yet a third process, which physicists call turbulent amplification, or turbulent dynamo. When the intergalactic gas falls towards the nodes of the cosmic web, it does not do so in a laminar and smooth manner. It falls from multiple directions at slightly different speeds, creating shear, creating turbulence. This turbulence shuffles the field lines in a specific way, a way that, for reasons having to do with the geometry of three-dimensional space and the Alpha-Venn helix, tends to amplify the field rather than destroy it. The field feeds the turbulence, and the turbulence feeds the field. A feedback loop that operates for entire geological eras and that can amplify a primordial field by many orders of magnitude. This is the amplifier. Not a single event, not an explosion or a collapse, but a slow, iterative, cumulative process. A dynamo that runs for billions of years using the most abundant fuel in the universe, which is the very movement of gas under the influence of gravity. The observable manifestations of this process are real, detectable, and some of them you can somewhat experience indirectly without needing any special equipment. just the patience to understand what is being measured. The most direct is Faraday rotation, the phenomenon where a polarized radio wave traveling through a magnetic field has its plane of polarization rotated. The more magnetic field along the path, the more rotation. By mapping the Faraday rotation of distant radio galaxies in different directions of the sky, astronomers build maps of the intergalactic magnetic field. These maps show something impressive. The field is not random. It has structure. It follows the filaments. It is aligned in ways that reflect the geometry of the cosmic web. There is also synchrotron emission, which is the light produced when relativistic electrons move in spirals along magnetic field lines. An electron moving in a spiral around a field line emits light, and the frequency of this light depends on the field strength and the electron's energy. This emission is visible in radio and in more energetic environments, even in X-rays. The filaments of the cosmic web, when observed at certain radio frequencies, glow with this synchrotron emission. They do not glow spectacularly like a nebula or a galaxy, but they glow enough that next-generation radio telescopes like LOFAR in Europe are beginning to map this subtle glow with increasing resolution. Another observable trace is the temperature distribution of the intergalactic gas. The warm-hot intergalactic medium, which astronomers call WIM, has temperatures ranging from 100,000 to 10 million Kelvin. The hottest part of this gas, the one that reaches tens of millions of Kelvin, is hard to explain solely by gravitational compression. Something additional heats this gas beyond what falling into gravitational wells would produce: Alphen waves, which are waves that propagate along magnetic field lines in a plasma, are serious candidates for this additional heating. They transport energy from smaller scales to larger scales in such a way that the magnetic field acts as a mediator, converting turbulence into heat in a distributed manner along the filaments. There is something in this story that resonates with much closer experiences. You have probably noticed that certain environments have a different quality of light, not because the light is objectively different, but because the air has a different structure, humidity, dust, temperature that organizes the propagation of a light in subtle ways. The intergalactic magnetic field does something similar to the particles and radiation that cross it. It does not stop them. It does not block them dramatically. It simply gives them a tendency, a statistical tilt in a certain direction, a preference for certain paths over others. And this preference, accumulated over distances of megaparsecs and times of gigayears, produces a universe structurally different from the one that would exist without it. The names astronomers use to classify the different regions of intergalactic space carry curious stories. The hot, diffuse intergalactic medium we mentioned, the WEM, was hypothesized before it was observed, a prediction made from the baryon budget, which is the name physicists give to ordinary matter, made of protons and neutrons. Cosmological models predicted there should be much more ordinary matter than was observed in galaxies and cold gas. This missing matter had to be somewhere. The hypothesis was that it would be in the filaments of the cosmic web, in the form of gas too hot and diffuse to be easily detected. The first observational confirmations came in the early 21st century, when X-ray and extreme ultraviolet satellites began detecting absorption by highly ionized oxygen towards distant quasars, exactly what would be expected from gas at temperatures of millions of Kelvin. The name WIM in English, which could be translated as caprice, has an unintended irony. The largest reservoir of ordinary matter in the universe was informally called a WIM before it was confirmed. Today we know it probably contains between 30 and 50% of all baryons in the observable universe, scattered in the filaments and their edges, invisible to visible light but traced in soft X-rays and ultraviolet absorption. There is also the Lyman alpha plasma, named for the hydrogen spectral line that is its main observational signature. When ultraviolet light from a distant quasar crosses a cloud of neutral hydrogen, it is absorbed at a specific wavelength. Over a path of billions of light years, this absorption occurs repeatedly, at different redshifts, creating what is called the Lyman alpha forest. a spectrum riddled with absorption lines that map the entire hydrogen structure along the line of sight. This method, refined since the 1970s, is today one of the most powerful tools for studying the intergalactic medium in cosmological epochs, much earlier than those we can observe directly in galaxies. Each line in this forest corresponds to a gas cloud at some point in space-time. Each cloud has a temperature, a density, a composition. Together, these lines are a stratigraphic archive of the universe, layers of overlapping information like the growth rings of an ancient tree, each recording the conditions at a different moment in cosmic history. There is also a more recent classification, the circumgalactic halos, which are the transition regions between a galaxy and the intergalactic medium proper. These halos, which extend for hundreds of kiloparsecs around each galaxy, are agitated, turbulent, crossed by galactic winds that expel gas enriched with metals, by accretion filaments that bring fresh gas from the intergalactic medium, by plasma bubbles inflated by supermassive black hole jets. They are regions of constant exchange, where the interior of a galaxy continuously negotiates with the exterior. The magnetic field in these halos is stronger than in the open intergalactic medium, but weaker than inside the galaxy, a smooth gradient zone that plays a central role in controlling how much gas enters and leaves each galaxy over time. You can experience something remotely analogous if you have ever stood on the outskirts of a city at night, at the point where the city lights begin to dissipate, but we have not yet reached the total darkness of the open field. This transition zone has a quality of its own. It is not city, and it is not nature. It is the region where the two systems exchange influence, where the heat accumulated by the pavements begins to mix with the cool air coming from outside, where the noise yields but does not completely disappear. Circumgalactic halos are like this, regions of transitory identity, neither entirely galaxy nor entirely void, where long-term destinies are decided. What makes this system collectively impressive is the appearance of equilibrium it maintains. The cosmic web we observe today seems relatively stable. The filaments do not collapse on themselves rapidly. The voids do not fill with gas perceptibly on human scales. Galaxies seem settled in their halos, accreting gas in a controlled manner, without global catastrophes. Everything seems as if it has reached a state of rest, or at least a very slow change. But this equilibrium, however convincing it may seem when we look at maps of the cosmic web, is profoundly fragile on scales that matter. The hot gas in the filaments is continuously losing energy through radiation. As it loses energy, it cools. As it cools, it can collapse. The magnetic fields that structure the filaments were generated by processes that depend on turbulence, and turbulence depends on moving gas, and moving gas depends on pressure gradients that continuous accretion feeds, but that any perturbation can modify. The heating sources, galactic winds, black hole jets, shock waves from galaxy mergers are intermittent and geographically localized events. They do not cover the intergalactic medium uniformly. They leave hotter regions and colder regions. They leave more magnetized regions and regions almost devoid of field. This apparent equilibrium is, therefore, an average. It is the result of many local imbalances that compensate each other on a large scale and over long temporal averages. Beneath the serenity of galaxy maps, beneath the elegant geometry of the cosmic web, there is a continuous agitation, a set of instabilities that sustain each other without ever fully resolving. And this agitation is about to be disturbed in ways that current models still cannot predict with confidence. There is a threshold that the intergalactic medium knows well, although astronomers are still learning to recognize it before it is crossed. This threshold has no visible shape, no boundary that can be marked on a map. It is a state of equilibrium that is maintained for hundreds of millions of years, and that, when it begins to yields in ways that rewrite the structure of entire volumes of the cosmos. The agitation that exists beneath the apparent serenity of the intergalactic medium is not a stationary phenomenon. It accumulates, it redistributes, and at certain moments, when the right conditions align in ways that depend on very specific local histories, It escapes the regime of small fluctuations and enters something completely different. The plasma that fills the filaments and the halos around galaxies is not a simple fluid. It is a magnetized fluid, with relativistic particles immersed in it, with temperature gradients that can vary by factors of tens over comparatively short distances, with magnetic fields that store energy and that can release this energy abruptly when the field lines reorganize. This type of fluid has instability modes that do not exist in common gases. It has modes in which the magnetic field amplifies small perturbations instead of damping them. It has regimes in which heat does not flow from hot to cold in an orderly manner, but redistributes in ways that depend on the geometry of the magnetic field, and that can create pockets of unexpectedly high temperature surrounded by much colder regions. One of the most studied instabilities in this context is known by the English acronym corresponding to magnetized buoyancy instability, but its mechanism is more intuitive than the name suggests. When a region of the intergalactic plasma is heated slightly above equilibrium, it tends to expand. If the magnetic field that permeates it is weak enough, it simply rises, like a bubble of hot air in a liquid. But if the magnetic field is strong enough and oriented in a particular way, the bubble does not rise freely. It drags the field lines with it, and in doing so creates a configuration where the magnetic pressure increases inside the bubble while decreasing outside it. This feeds back the original perturbation. The bubble grows larger, the field inside it intensifies more, and what started as a small thermal fluctuation transforms into a structure that can grow to scales of tens of kiloparsecs before other mechanisms begin to resist the growth. This type of process is not merely theoretical. X-ray observatories studying galaxy clusters have revealed structures that seem consistent with instabilities of this type in advanced stages. They are temperature ripples in the intergalactic medium of clusters. They are heat fronts that move in ways that do not correspond to the obvious mass movement of the gas. They are filaments of slightly cooler gas that persist within much hotter regions for much longer periods than simple physics would suggest. Each of these observations is a window into the internal dynamics of a fluid that, seen from afar, seems just a diffuse X-ray luminous cloud, but which inside is in a state of structured convulsion. The most dramatic threshold, however, is what happens when gas accretion onto a galaxy increases abruptly enough to awaken the supermassive black hole at its center in a way that escapes the smooth feedback regime. Models show that there are two distinct modes of activity for an active black hole in a galactic nucleus. In the mode called the quiescent state, the black hole accretes relatively little gas, releases energy mainly in the form of collimated relativistic jets, and the effect on the surrounding intergalactic medium is a gradual pressurization that prevents excessive cooling of the gas. It is the regime that maintains equilibrium. It is the mechanism that galaxy formation models needed to invoke to explain why massive galaxies stop forming stars. But there is another mode. When the accretion rate exceeds a certain threshold, the accretion disk around the black hole changes configuration. It goes from a geometrically thin and optically thick disk to an inflated geometrically thick structure, which radiates in very different ways. In this regime, the luminosity of the nucleus can increase by factors of tens or hundreds in astronomically very short times. The winds leaving the accretion disk stop being collimated and become almost isotropic. A very significant fraction of the rest energy of the gas falling into the black hole is converted into radiation and kinetic energy of the wind, and all this is deposited into the intergalactic medium around the galaxy in times that can be just a few 100 million years. What happens to the intergalactic medium when a quasar turns on this way is one of the most energetic phenomena in the cosmos accessible to observation. The shock front that the relativistic wind creates when it encounters the cooler gas of the galactic halo travels outward at speeds of thousands of kilometers per second. When this front reaches the gas in the filaments feeding the galaxy, it does not just heat the gas, it compresses it, creates turbulence on scales ranging from parsecs to megaparsecs, and seeds magnetic fields along the entire extent of the disturbed filament. The gas that was flowing smoothly inward along the filament is accelerated outward for a few moments, then decelerates, and spends years or tens of millions of years in a highly heated, turbulent state before beginning to cool and try to resume collapse. Humanity began observing these events in detail with X-ray telescopes like Chandra and XMM Newton, which revealed cavities in the intergalactic medium of clusters, hot plasma bubbles created by the jets of central black holes, and shock fronts that correspond to supersonic sound travelling through the cosmic fluid. But these observations capture only the latest stages, the signals that persist for hundreds of millions of years after the initial event has already died out. To see the event itself, one must observe distant quasars, which correspond to cosmological epochs when the galaxy merger rate was much higher, and therefore the conditions to awaken supermassive black holes were much more common. There is something profoundly asymmetric in time when thinking about these phenomena. The light that reaches an X-ray detector today and shows a clean, almost empty cavity in the intergalactic medium of a cluster a few hundred megaparsecs away left there a few 100 million years ago. The event that created that cavity, the quasar ignition, the shock front, the compression of the filaments, happened even earlier. What is observed is a kind of energetic archaeology. Astronomers read the structures that persist in the gas as if reading ruins, trying to reconstruct the sequence of events that created them. To measure these phenomena more directly, there is a set of techniques that have become increasingly sophisticated in recent decades. The Sunyaev-Zeldovich effect, by which the cosmic microwave background is slightly distorted when it passes through the hot gas of the intergalactic medium of clusters, allows mapping the total pressure of the gas in ways that complement X-ray observations. Radio telescopes detect the synchrotron emission of relativistic electrons in the diffuse radio halos that many clusters possess, revealing where turbulence injected energy into high-energy particles and where magnetic fields have the intensity needed to produce detectable emission. Optical spectrographs measure the velocities of ionized gas along lines of sight that cross intergalactic filaments, and the width of the spectral lines reveals how much turbulence exists within the sampled gas volume. But the most dramatic phenomena leave signatures that none of these techniques can fully capture alone. The merger of two massive galaxy clusters is perhaps the most energetic event in the post-Big Bang universe. When two clusters collide, each carrying hundreds or thousands of galaxies immersed in dark matter halos with masses of tens to hundreds of trillions of solar masses, what happens between them over a period of about 1 billion years is a transfer of gravitational energy to the intergalactic medium on an unimaginable scale. The dark matter halos pass through each other almost without interacting, because dark matter is collisionlessly cold. The galaxies also pass through with few direct collisions because the space between them is vast, but the gas in the two halos collides directly, and the result is a shock wave that can have speeds of several thousand kilometers per second and that heats the gas in the intergalactic medium of the resulting system to temperatures of tens of millions of degrees. While you rest somewhere in the Coma cluster, at a distance of about 100 megaparsecs from here, a shock front that has existed for hundreds of millions of years continues to propagate through the gas. The gas ahead of it, not yet shocked, is at a temperature of a few tens of millions of degrees and moves slowly towards the gravitational center of the cluster. The gas immediately behind the front where the shock has passed is compressed to several times the original density, heated to hundreds of millions of degrees and turbulent on all length scales from parsecs to megaparsecs. The magnetic fields in this region were amplified by the shock and the resulting turbulence to values far above those that existed in the unperturbed gas. And throughout this turbulent region, electrons are being accelerated to relativistic speeds by the Fermi mechanism, bouncing repeatedly through the shock front and gaining energy with each crossing, until some of them have energies large enough to emit radio waves visible from here. This type of structure, called a radio relic, is one of the most direct pieces of evidence that cluster mergers transform the intergalactic medium in ways that persist far beyond the event that created them. A shock front that has travelled for megaparsecs and continues to accelerate particles is a cosmic high-energy machine that runs without apparent fuel, because the fuel is the gravitational energy of the merger that continues to convert into flow velocity and then into heat and accelerated particles. And this machine seeds the intergalactic medium with magnetic fields, with relativistic particles, with filaments of compressed gas that can persist for billions of years after the resulting cluster has again reached a state of apparent equilibrium. What humanity still does not know, and that current models cannot predict with confidence, is how these dramatic events communicate with the wider cosmos around them. A cluster merger does not happen in a cosmic vacuum. It happens at a node of a web surrounded by filaments that feed it and that transport gas and galaxies from very distant regions. When the merger injects energy into the intergalactic medium of the cluster, part of that energy travels outward along the filaments. Part of the turbulence generated in the cluster propagates into the gas of the connected filaments. The magnetic fields that were amplified by the shock can be transported outward, along with the gas that flows back into the filaments after the merger. This means that the most dramatic phenomena that happen in the densest nodes of the cosmic web do not remain confined to those nodes. They radiate in ways that current telescopes can barely detect into the filaments that connect those nodes to the rest of the cosmos. And these filaments are in turn the same structures that connect smaller groups of galaxies, that connect isolated galaxies, that eventually connect everything that exists in a network that has no truly disconnected regions. An event that happens in a massive node hundreds of megaparsecs away can send magnetic perturbations, pressure waves, relativistic particle flows along filaments that eventually reach the halo surrounding the local group. The cosmos is not a collection of separate events. It is a system in which every perturbation, however localized it may seem, has consequences that propagate further than simplified models suggest. The web that connects the cosmos to itself is not a passive adornment of the universe's structure. It is the circulatory system through which the universe still breathes, still grows, still redistributes what it has produced over billions of years of gravitational and thermodynamic evolution. When we think of intergalactic filaments as simple bridges of matter between clusters, we are dramatically underestimating the role these structures play in the ongoing life of the cosmos. They do not just connect, they mediate, filter, amplify, and feed back. Each filament is simultaneously a transport channel and an active participant in the processes that shape what is inside it. The most intimate partner of the intergalactic filament in this dance of exchanges is the diffuse gas that fills it. That hot, faint plasma we call the warm, hot intergalactic medium, or more precisely filament gas, which exists at temperatures ranging from 10,000 to 10 million kelvins, depending on local density and proximity to more energetic nodes. This gas is not in equilibrium. It is perpetually being heated on one side and cooled on the other, compressed by gravitational tides in some regions and expanded by radiation pressure in others. The relationship between this gas and the galaxies residing in the filaments is one of reciprocity that astronomers took decades to begin to understand properly. Galaxies consume the filament gas, which falls towards the galaxies through slow, continuous accretion. But galaxies also return to the filament everything they could not retain. Galactic winds loaded with heavy metals forged in stars, ultraviolet radiation produced by young populations of massive stars, particles accelerated by supernova explosions that escape beyond the galactic halo and dissipate into neighbouring filaments. This exchange cycle is not linear or simple. When a galaxy consumes gas from the filament, it accelerates star formation inside it. Massive stars live short lives and end in supernovae that heat the interstellar medium of the galaxy itself, sometimes so violently that part of this superheated gas is expelled out of the galaxy, back into the filament in the form of a galactic wind. The filament then receives back material that is chemically richer than what it provided, but also hotter and more turbulent. This alters the conditions of the filament, making it harder for adjacent gas to cool and fall back towards the galaxy. The galaxy, having heated its own fuel supply, it experiences a reduction in the star formation rate. The system self-regulates, but never precisely, never in a way that produces perfect stability. It produces instead oscillations, cycles that succeed each other on timescales of tens of millions of years, during which the galaxy alternates between phases of intense activity and phases of relative quiescence. The supermassive black holes residing at the centers of the most massive galaxies add another layer of feedback to this system. When they accrete matter, they launch plasma jets at relativistic speeds that propagate for hundreds of kiloparsecs, sometimes penetrating deep into the filaments that link the host galaxy to the rest of the web. These jets inject kinetic and magnetic energy directly into the intergalactic medium. Kinetic energy converts to heat through shock waves. Magnetic energy amplifies pre-existing magnetic fields in the filament, creating helical structures that persist for billions of years after the jet has ceased. A single active episode of a quasar can magnetize a volume of the intergalactic medium that would be impossible to magnetize by any other known mechanism on any reasonable timescale. And once magnetized, that volume of the filament behaves differently forever, as magnetic fields influence how gas flows, how high-energy particles propagate, how turbulence develops. On short timescales from decades to centuries, what we observe from the outside is just a static slice of processes that unfold much slower than any human instrument can track in real time. When we point a telescope at an intergalactic filament and measure the gas temperature, the density of free electrons, the presence of weak magnetic fields, we are capturing a snapshot of a system that has changed imperceptibly since the light we are detecting left there. The light we see from a filament 50 megaparsecs away left there over 160 million years ago. The filament we are observing is the filament of the late Cretaceous, from the time when dinosaurs still walked the Earth. Today's filament, the contemporary filament, is invisible to us in the most literal sense possible. On timescales of centuries, what changes inside an intergalactic filament is practically undetectable, even with the most sensitive instruments humanity could build in the near future. The processes of gas exchange between galaxies and filaments occur at rates of tens to hundreds of millions of years. Magnetic perturbations propagate along filaments at speeds much lower than that of light, taking entire geological eras to cover distances that light would cross in millions of years. A shock produced by the merger of two massive clusters today will take hundreds of millions of years to propagate along a filament and measurably influence the galaxies at the ends of that filament. The universe operates on a time register that makes the entire human existence, the whole history of our species, the entire duration of our civilization, something closer to an instant than to anything we could call duration. On timescales of millions of years, filaments grow. The expansion of the universe stretches the distances between the nodes of the web, and the filaments connecting them become progressively longer and fainter. The gas residing in these filaments dilutes as the volume containing it increases. The average density drops. The galaxies residing in the filaments become progressively harder to feed as the gas reservoir that nourished them spreads over larger volumes that are more difficult to accrete gravitationally. In billions of years, the filaments we know today will be much rarer structures in terms of gas content, although the underlying dark matter web will persist, as dark matter does not interact with expansion in the same way as gas. The dark matter web will grow, but the luminous web, the gas, the galaxies, the activity we can detect will progressively fade. Sensitivity to initial conditions is one of the most profound and humbling aspects of any attempt to model the cosmic web system. Large-scale structure formation simulations, those that reproduce with extraordinary fidelity the observed distribution of galaxies and filaments in the universe we know, are extremely sensitive to the conditions prevailing in the first moments after the universe's emergence. Small variations in primordial density fluctuations, in the proportions of different forms of matter and energy, in the intensity of primordial magnetic fields, produce universes that evolve differently in their large-scale structures. Not radically different in their general aspects, but different enough in their details that the filaments that emerge the galaxies that form, the nodes that grow, are distinct in their most specific details. This means that even knowing perfectly the physics that governs the universe, which is far from being the case, we could never predict with absolute precision what the exact structure of the cosmic web would be from the initial conditions, because the initial conditions themselves have fundamental uncertainties that amplify over billions of years of evolution. The cosmos is sensitive to its own origin in a way that makes any deterministic prediction of its details an illusion. What physics can offer are statistical distributions, probabilistic statements, general understandings of mechanisms, but not exact descriptions of every individual filament, every galaxy in every node, every magnetic field in every region of intergalactic space. There is a fundamental limit to our ability to know the universe in detail that is not just a technological limit. It is a limit that emerges from the profound nature of the system itself. And yet, within that limit, what has been achieved is extraordinary. Humanity started from an existence that did not even have the notion that the spiral nebulae seen in telescopes were external galaxies, systems comparable to ours, and in less than a century reached a detailed understanding of the cosmic web, simulations that reproduce its structure with remarkable fidelity, indirect detections of the gas filling intergalactic filaments, measurements of weak magnetic fields that exist between galaxies. This progress was not linear. It was punctuated by conceptual revolutions, by discoveries that forced a complete revision of models that seemed solid, by the realization that the universe was consistently more complex, more subtle, more interconnected than any previous generation had imagined. There is a specific beauty in this position of partial knowledge. Physics has given us access to an understanding that is genuinely profound, that captures real mechanisms, that allows predictions that are impressively confirmed in independent observations. But this same understanding reveals, with each new layer uncovered, an additional complexity that was hidden beneath the previous layer. Every answer generates more refined questions. Every more sensitive instrument detects details that existing models did not perfectly predict. The universe never becomes less surprising as we know it better. It becomes differently surprising in subtler, deeper, more mathematically sophisticated registers, but no less admirable for it. The space between us and the next galaxy is simultaneously the most well-studied region of the universe in terms of large-scale structure and one of the most difficult to observe directly in its details. We know it is not empty. We know it is the fabric on which the history of the cosmos is inscribed. We know that the filaments crossing it transport memories of events that happened billions of years ago, in the form of magnetic fields, heavy metal distributions, pressure perturbations that propagate in slow motion along structures that are longer than the human mind can truly visualize. We know this space is not separate from us. We are part of the same system. The halo of the local group is immersed in the same intergalactic medium that fills the filament to which we belong. The magnetic fields that exist between the galaxies of our group are continuous, in some sense, with the fields that exist further away, in the filaments linking the local group to the Virgo cluster, and beyond. And when one rests in this perception, when one allows it to settle without haste, something emerges that is hard to name precisely, but that is perhaps the most characteristic sensation of cosmological thought in its most profound form. The sensation that beneath all this complexity, all these feedback cycles, all these systems interacting with other systems on scales ranging from the microscopic to the cosmological, there is something that is simple, not simple in the sense of easy, not simple in the sense of banal, but simple in the sense of unified, coherent, that all these different manifestations arise from something that precedes and contains them all. The filaments, the gas, the magnetic fields, the dark matter, the galaxies, the black holes, the winds, the supernovae, the expansion of space, the web that connects everything. All this seems to be the elaborate expression of something much more fundamental, something that physics has not yet fully captured, but that existing equations tangent in ways that make physicists feel they are close to something. And perhaps it is exactly there, in that sensation of proximity, that the journey between us and the next galaxy reveals its most unexpected dimension. It is not just a matter of distance. It is not just a matter of matter and energy distributed across volumes that defy any human intuition. It is a matter of deep structure, underlying pattern, of something that repeats on such different scales that the repetition itself becomes the main message. The feedback processes that govern intergalactic space are, in their essence, conversations. They are dialogues between forces that respond to each other through time and space in ways that neither party isolated could predict or execute. When a galaxy launches a wind of plasma heated by its active nucleus, this wind travels through the filaments, compresses the gas along the walls of the great cosmic structures, cools regions that were about to collapse into new stars, and in doing so alters the mass distribution that in turn modifies the gravitational fields that in turn affect the trajectory of the very winds that came before. Every cause becomes the effect of effects it itself generated in cycles that extend for hundreds of millions of years. And the universe, in this sense, has memory. It carries the records of every interaction in its current geometry, in its temperatures, in its densities, in its fossilized magnetic fields that still today hold the signature of events that happened before the Earth existed. What stabilizes this system is not an external force governing it from the outside, but the very internal structure of the cycles. When heating becomes excessive, pressure increases and prevents the formation of more stars that would produce more heat. When cooling advances too much, gas collapses, forms stars, which explode and heat the medium again. It is an emergent stability, not imposed, not planned, but that arises naturally from the physics that connect every component to every other component through bonds of influence that cross and compensate each other over scales that the human mind cannot visualize directly, only describe mathematically and then contemplate with a kind of silent reverence. The molecular dimension of this space that seems empty is, perhaps, the most surprising of all. When one thinks of the intergalactic void, the instinctive image is of nothing. But what exists between galaxies includes molecules, not in abundance comparable to stellar nebulae, not in densities that would produce life or worlds, but in traces that modern spectroscopy can detect in the spectra of distant quasars seen through these immense spaces. Molecular hydrogen, ionized carbon, oxygen in ionization states that reveal the temperatures and densities of the filaments containing them. These molecules are messengers. They carry in their chemical composition the history of the environments they pass through, the supernovae that forged their atoms, the stars that enriched them with heavier elements, before dispersing them into the interstellar medium and from there into the intergalactic medium through winds and ejections. The carbon floating in the filaments between our galaxy and Andromeda was forged inside stars that existed and died before our solar system existed. The oxygen found scattered in this intermediate space went through generations of stars, was processed, expelled, captured, reprocessed, and finally sent to the intergalactic medium by explosions that released energy equivalent to the energy our sun will emit during its entire life in fractions of a second. These atoms carry in their quantum properties the memory of temperatures of tens of millions of degrees, of pressures that would crush any macroscopic structure into unrecognizable configurations. And now they float in silence at temperatures a fraction of a degree above absolute zero, waiting for the next cycle, the next compression, the next star that will call them back to its nuclear dance. As an integrated system, the space between us and the next galaxy has no clear borders. It begins where the influence of our galaxy weakens enough for other fields to dominate, and this weakening is gradual, continuous, without a precise cut-off point. The dark matter of our galaxy extends far beyond its visible disk and stellar halo, in a diffuse structure that intertwines with the dark matter of other galaxies in the local group, and beyond them, with the filaments that make up the cosmic web on even larger scales. There is no where our galaxy ends and intergalactic space begins. There is a transition, a zone of decreasing influence, a gradual dissolution of identity that is itself part of the structure that connects everything. The magnetic fields permeating this space are the most mysterious element of this systemic view. They do not follow borders. They cross from galaxy to galaxy along plasma filaments, connecting structures separated by distances of hundreds of thousands of light years, as if they were invisible threads of a tapestry that no observer could see completely from within. And these fields influence the movement of cosmic rays, which are very high-energy particles travelling through the universe in helical trajectories determined by these fields, eventually reaching the atmospheres of planets like Earth and interacting with nitrogen molecules to create new elements that fall like radioactive rain on the planet's surface. Intergalactic space touches Earth through these particles that it guided for millions of years in trajectories that classical physics could not calculate without the complete map of every magnetic field they encountered along the way. Emergence is perhaps the most powerful concept that intergalactic space can teach. Simple rules, applied consistently in a sufficiently complex system, produce patterns that the rules themselves do not explicitly contain. Gravity alone attracts mass to mass with a force proportional to the product of the masses and inversely proportional to the square of the distance. Simple, but applied to billions of dark matter particles interacting over billions of years, this simple rule produces filaments, nodes, voids, superclusters, the cosmic web in all its immense and intricate complexity. The rule does not say to make filaments. The rule does not know that filaments exist, but filaments inevitably emerge from its repeated application in a universe with the initial conditions ours had. Similarly, the equation describing how a plasma cools when it loses energy through radiation is a local equation without an overview, but applied simultaneously to all the gas in an intergalactic filament, it produces the multi-layered structure we observe, with a cold, dense core surrounded by progressively hotter and more diffuse layers that dissolve into the surrounding void. The structure emerges, the pattern arises, organization appears without anyone having organized it, because organization is what happens when simple physics operates with enough freedom and enough time. Deep down, what lies between us and the next galaxy is simply the universe learning to know itself through structure. Every filament is a connection the universe establishes with itself. Every atom of gas scattered in the void is the universe in transit, between one form and another, between one star and the next. Every magnetic field is the universe writing on its own fabric, the memory of processes that have already ended but whose consequences still travel. Dark matter is the universe in its most silent form, present everywhere but communicating only through the curvature it imposes on space. Galaxies are the concentrated, organized, luminous, expressive universe, and the void between them is the universe in its most expanded, quietest, most patient form. Every element we traversed in this journey reconnects to this single principle. The filaments we mapped in the early parts are the pathways through which the universe moves between its nodes of organization, channels of exchange between concentrations of existence. The intergalactic gas we described in its temperature and density is the universe in a state of potential, neither so cold that it collapses nor so hot that it disperses completely, suspended in a dynamic equilibrium that is the condition of possibility for everything that will come later. The dark matter that silently structures everything is the grammar of the universe, the set of invisible rules that determines which forms are possible before any specific form is chosen. Magnetic fields are the memory of the universe, records in the form of force of everything that happened and that continues to influence what happens now. And we, here, on the planet orbiting an ordinary star in a spiral arm of a galaxy, that is itself just one node among hundreds of billions of other nodes in the cosmic web, are the universe looking at itself with eyes it built itself over nearly 14 billion years of growing complexity. This is not a poetic metaphor, it is a literal description. The atoms forming our neurons were forged in stars. The energy that moves them came from the sun. The structure of our solar system was determined by the dark matter filaments that collapse to form our galaxy. We are the direct consequence of everything that happened before, and when we look at intergalactic space, we are looking at the context that made us possible. There is something profoundly reassuring in this perception when it truly settles. We are not aliens in the universe. We are not exceptions or anomalies or improbable accidents that exist despite the cosmos's indifference. We are an integral part of the same structure that forms the filaments and the voids and the magnetic fields and the plasma winds. We are made of the same materials, governed by the same forces, participating in the same cycles on different scales. The same physics that makes intergalactic gas organize into filaments makes neurons organize into networks. The same gravity that collapsed primordial gas into stars collapses eyelids when the body decides it is time to rest. And now, at this moment, while the night advances in silence around you, the universe continues. The filaments continue to flow with their invisible plasma. The magnetic fields continue to guide particles in helical trajectories between galaxies. Dark matter continues to curve space with its silent presence. Distant supernovae continue to see the intergalactic medium with atoms that will wait for hundreds of millions of years before becoming part of something new. Everything continues. The universe does not need your wakefulness to move forward. It took care of itself for billions of years before you existed, and will continue taking care after. You can rest. You are safe. The space between galaxies is immense and silent, and this silence is not threatening. It is the stillness of something that is exactly where it should be, doing exactly what it must do. You are also exactly where you should be. The universe takes care of you. It always has, from the instant the first hydrogen atoms formed and began the trajectory that would lead, through stars and explosions and planets and oceans and billions of years of patience, to this moment, this body, this consciousness that now rests. Everything is in order. The filaments flow. The magnetic fields persist. The galaxies spin in their smooth orbits around the nodes of the cosmic web. The expansion of space continues its gentle course. Nothing is broken. Nothing is lost. The structure that sustains everything is intact, as it has always been. While you rest, intergalactic space continues its silent exchange of matter and energy between galaxies. It continues without haste. It continues without noise. It continues with the patience of something that has billions of years and billions more ahead. You are part of this. You always have been. The filaments dissolve now in your mind like mist clearing with the soft heat of the morning yet to come. The magnetic fields become lines of peace running through your sleeping body. The dark matter around you silently supports the floor beneath you, the walls around you, the air you breathe with an increasingly slow and deep rhythm. Distant galaxies continue their smooth spin, indifferent to time, patient as only the eternal can be patient. You breathe. The universe breathes with you. Your body is heavy and warm and completely safe. Your thoughts become less defined, less urgent, less distinct from one another. They dissolve like gas dissolves into the intergalactic void, expanding softly until their edges disappear, and there is no longer a difference between the thought and the silence around the thought. There is only stillness now. There is only the vast tranquil space between one galaxy and another, between one thought and the next, between one breath and the following. This space is yours. It has always been yours. It is the place where rest dwells, where consciousness goes when it finally allows itself to let go of the weight of knowing and doing and watching. Let go. The universe is on guard tonight. It always is. The universe continues its silent dance, and we rest in its embrace. Thank you for walking with me tonight. Sleep well.